Okay, hello. Thank you again for your kind invitation and for your patience to hear me the second uh, time. So last time I just spoke about the Bessel equation in different uh, versions, and mainly I was interested in the approach to solutions, to analytic solutions of this equation which satisfy, I mean, analytic solution to corresponding eigen problem, and these eigen solutions with eigenvalue equal to one. I suppose they satisfy this beautiful. I suppose I will show you that they satisfy this beautiful property that they are in some sense form uh, functional associative commutative algebra, where the role of structure constant plays so-called multiplication kernel. This philosophy goes to very, very old tradition to study products for special functions, and this tradition goes back to 19th century to special functions which are solutions of Bessel equation, of different degeneration of hypergeometric equations. And what I want to show you that these uh, solutions of my equation, which I try to convince you that this equation is extremely important. This equation, first of all, important because it is classical, classical generalization of usual Bessel equation, and second, because it plays a very, very important role in so-called mirror symmetry in the approach of Sasha Giventhal, and he proved that the solution of this equation plays a role of some generating function for so-called uh, Gromov-Witten invariants. I will not repeat it, and I will not go to more details. And also another interesting part of the story, which probably I will touch a little bit, that this solution related to two classes of symmetric polynomials with three generators. The polynomials of this type, uh, just I want to draw your attention that these polynomials are this discriminant type. You see, it's a discriminant of some quadratic equation, and sigma for brevity, I denote just a classical symmetric functions of x, y, and z. And second class of the equations, so-called generalized conceptual polynomials, they are also polynomials which are discriminant of this quadratic equation, slightly different. So if you compute in full um, coordinates in C3, x, y, z, you will see that this polynomial is total degree 6, and this polynomial in x, y, z is total degree 4. But both polynomials, they are symmetric, it is clear, but they are also can be written in each single variable as a quadratic polynomial. And then they have some mutual properties, and these mutual properties indicate that this polynomial should somehow should be related, and that's the subject of another story. I spoke, by the way, a lot about this story 1.5 years, and I will not probably come back to this. This I showed you last time. This typical product formulas, classical product formulas for hypergeometric and degenerated hypergeometric functions. For me, it is a very important product formula for Besselland function of degree 0. first kind Bessel functions, which are solutions of classical Bessel equation. And for this equation, my kernel has this nice algebraic form. As for Kontsevich, so this I will show you that this nice algebraic form, it is a simplest form of this first class Buchstaber polynomial. And also generalized Kontsevich polynomials, they also can be written in the form of algebraic multiplication kernel, where this Kontsevich polynomial constructed as a discriminant of quadratic trinom, and this quadratic trinom obtained if you take this cubic and consider the following differential equation, which is people call small V or D2 equation, but it is a special case of, for those who are in the business, it's a special case of so-called Hoyne equation. Anyway, this I just had some motivations from initial Kontsevich approach. This I didn't tell you about this links of this polynomial to so-called two-valued groups, and this I will have no time probably, but I will try to come back if I have time. And then I explained you that there is a serious motivation to study monodromy and solution behavior for these polynomials from the perspective of so-called Calabi-Yau differential operators. This is another part of the story of mirror symmetry, and this part of the story relates to so-called period functions, which are periods of related to integrals of the family of top forms for Calabi-Yau, and these functions satisfied to some special class of differential equations with respect to algorithmic derivative. People call this class Calabi-Yau differential operators, and my talk last time stopped at these operators have very important property. This important property, they have maximal unipotent monodromy in the origin. It means that the Jordan block of this monodromy matrix in the origin, it's a upper triangular matrix with the unities on diagonal, and all other over diagonals, which they have a coefficients of exponential development. So the first upper super diagonal is 1/2, second 1/3 factorial, and etc. Until the and 1/k factorial, with k times k the size of this monodromy matrix. This property is beautiful because it gives a very, very explicit and simple form for so-called fundamental basis of Frobenius type. It means that the first function in this fundamental basis is always analytic function, phi 0, and other basis functions they explain as a combination with coefficients depending on degrees of logarithm. And all these functions, you can explicitly write the sum of analytic function plus analytic function times logarithm plus another function, which can be written in its turn for second function enters as a coefficient of logarithm square, and etc. and etc. So this is a very special basis. I will show you this again in the example. This type of differential operators, Calabi-Yau differential operators, they comes from, for example, from Calabi-Yau varieties. In the dimension 1 in elliptic curve, they are this period function. They satisfy so-called Picard-Fuchs equation. I have a choice of different representation of elliptic curve. If I have this dependence on t, then this equation, its equation with respect to this parameter t variable, and this equation, it's a result that on the elliptic curve there is only one holomorphic differential, and if you take this integral by two periods, they satisfy some relation of second order differential operators. A similar story in the degree in the dimension 2 K3 surface, dimension 2 Calabi-Yau variety. So you have some lattice here. Here it was a standard lattice for the case of elliptic curve. In the K3, it's a lattice which is much more complicated. You have a huge lattice or dimension 19 or dimension 21, and in this lattice you can also integrate just some top form, which is a form on two-dimensional, two form in this case, and the integrals satisfy the cubic relation. So this, you have a huge lattice, but the relation includes degree 3 differentials of this function of period. And for n equal to 3, which is the most interesting because it's three-dimensional Calabi-Yau, which physicists are interested in more eagerly, because it is this reducible dimensions, 6 real dimensions, which you need to reduce to have our 4 dimensions from, say, 10-dimensional M theory or something like this. Anyway, it is most interesting for physicists to study Calabi-Yau structures on 3-dimensional complex varieties with top holomorphic 304. This story in 80s was just enormously developed due to Yau, Witten, and many other young and not very young physicists and mathematicians, and they found thousands of different Calabi-Yau. It means that the structures of Calabi-Yau they are huge. It's even physicists called it zoo. It was a zoo, and so people needed to study more precisely this zoo. And one of the most famous Calabi-Yau of dimension 3, so-called dwarf quintic. It is a minimal deformation of this Fermat quintic with the parameter t, and this three-dimensional Calabi-Yau manifold admit the corresponding equation on the Calabi-Yau on the period. So it's Calabi-Yau operator of degree 4. And then it was the most exciting result in mirror symmetry that this operator, which for this quintic threefold was computed, this operator has a very nice first analytic solution in Frobenius basis. This first analytic solution is integral, and then if you go to the second solution, phi 1, then it looks like this analytic times logarithm, as I explained, because in zero this operator has uh, maximum important monodromy. So, and this part phi 1 unfortunately is no more integral, but Yao and Yan, they introduced new coordinate, new variable q, which depends on our old t, is exponential of ratio phi sub 1, phi 0. And this new series q starts with t and also have mercury integral coefficients. Then, because it starts with t, Yang and Yao made so-called mirror transformation, and they called this coordinate canonical coordinate, and they inverted this series and obtained series T of Q, which is only rational, not no more integral. But if you rewrite the Frobenius basis in new coordinate Q, then this can play the same game. It means just go to ratio phi 0, phi 0, 1, phi 1 to phi 0 log Q, phi 2 to phi 0, 1 over 2 log Q square, and then the series in power series in Q with no more integral coefficients. They discovered that if take this third ratio, phi 2 to phi 0, in fact, first it is 1, second it is logarithm, and this complicated series which starts with logarithm square and derivative 2 times logarithmically, then you obtain again integral integer coefficients, and this property of integrality they called the corresponding series Yukawa coupling. It relates to Yukawa coupling in physics. How it relates, I will not explain at the moment. And they discovered that, moreover, it is not only integral as a series in Q, but if you write this Yukawa series in so-called Lambert series form, so it means degrees of Q, you write it as a series in this rational function in Q to K over 1 minus Q to K with some coefficients divided by 5. Then these coefficients up to this common factor 1 over 5, they are always integer, and coefficients, so they have a common factor k to 3 to each k, and n sub k, they have very, very interesting numerological meaning. Namely, people knew this when physicists computed, they knew these two numbers, and they say, oh, we know these numbers are classical geometric invariants. They are numbers of degree 1 and degree 2 rational curves in which are lying on the generic degree 5 threefold in P4. So physicists compute many coefficients. So the next coefficient was unknown, but supposedly this should be number of cubics. And this confirmation of physics conjecture, of this physics computation, mathematically was done in works of, in paper of Ellingsrud and Ströme, Norwegian algebraic geometers. They used localization formulas to prove that really, if you take degree 3 curves on quintic threefold in P4, then it corresponds to this number which Lian and Candelas and collaborators obtained. So was conjectured that all these coefficients, they have this numerological meaning. And why it is exciting? Because on the other hand, people knew from Kontsevich, Witten, and Manin computations that these invariants, they are so-called integral Gromov invariants, which can be obtained in the proof of Kontsevich proof of Witten conjecture for generating function of KDV hierarchy tau function. And then this beautiful theorem that it is not only first three, but all of them, they were confirmed by Giventhal and independently by Lian, Liu, and Yao. So they proved that indeed Gromov-Witten invariant gave the same instanton numbers. So this theorem is called mirror theorem, and in fact it compares two invariants in two sides of mirror conjecture. So you know that mirror conjecture that there are two classes of Calabi-Yau threefolds in A side and B side, and correspondence of these computations and Gromov-Witten invariants, it's just this correspondence between data from one side of mirror symmetry to of mirror Calabi-Yau and to other side of mirror symmetric Calabi-Yau. Anyway, this was very well known at least in early 2000. And then people immediately started to try to find another Calabi-Yau differential operators. First of all, of course, Calabi-Yau. I told you that there are many Calabi-Yau structures, there are many Calabi-Yau manifolds. Topologically, they are very similar, but for example, in the case of K3, they are all diffeomorphic, but complex structures are different because of this Dalibor homology and Hodge, different Hodge numbers. So, for example, people started to describe different classes of n equal to 4 Calabi-Yau differential operators. It means that they started to study differential operators with, which are monic with respect to this logarithmic theta. They have only regular singularity in origin, and then this origin is a maximally unipotent point in the sense which I explained you. Also, they are self-dual, which is less important, but it is always like this in the usual sense of differential operator conjugation. And what is important that they are all satisfied to the following integrality conditions. So if you write these Frobenius solutions, so the holomorphic solution always integral. If you take the mirror coordinate, which is exponential of the ratio, you have this integral coefficients as well. And then when you take mirror transformation, go to this Q coordinate, take Yukawa series in Lambert form, you obtain these instanton numbers. They are always should be also integer. So this was the hunting of these operators. And many people computed the whole database of these operators. So now, if you say have some interest in arithmetic series, you can try to check if it is really relates to some good solution of some differential operators, Calabi-Yau type or almost Calabi-Yau type. You can go to homepage of Duka van Straten in Mainz and to try to substitute your series and check if it is or satisfy to some good differential operator. So what people usually do. Another interesting side of this story, of course, that if you take your solution phi zero, which is analytic solution of Calabi-Yau differential operator, then it can be written in integral form like residue of the following top form. It is integral over product of spheres, and this integral of the product of spheres, it means that it's integral over torus. You take the toric measure, d log, d log, d log, in n number of variables, and your singularity, it is zero locus of the following function, which is given by Laurent polynomial, which depends on x1, xn, or over 1 over x1, 1 over xn. And to get this, you just need to write this as a series, power series with coefficients bk, and this coefficients bk, it is just the residue. It means that this is the 0 degree coefficients, constant coefficients of case degree of your Laurent polynomials. Such integrals and such periods, they appeared in so-called Landau-Ginzburg models. It's an alternative. There is in physics there is so-called Calabi-Yau-Landau-Ginzburg correspondence. It means that how to get the Calabi-Yau varieties. Sometimes people take these toric varieties given by these Laurent polynomials, or these hypersurfaces in product of spheres in torus. And then after good compactification, from time to time it's happened that this compactification of these toric surfaces, it gives you Calabi-Yau. So this usually people call it Calabi-Yau Landau-Ginzburg correspondence. These Landau-Ginzburg models, it is really relates to Landau and Ginzburg and to some physical models, which I will not explain now. It's you ask Losif, Andrei Losif, he's a big expert in this. He can explain it very in a simple way to mathematicians. So I stopped last time at that point. And then now I want to start my story about Bessel again. Because Bessel operators, they are not Calabi-Yau. What we did with my colleagues, with Duka and with Ilya, we studied these multiplication kernels for Bessel operators, for Bessel functions, and studied the equations which this kernel satisfies. And it's happened that this equation behaves like Calabi-Yau equation. So it's again differential operator solution to this kernel. So you can prove that this kernel satisfies to some differential equation, and this differential equation sometimes behaves like Calabi-Yau differential operator equation. But it is not Calabi-Yau. But it is close. And this equation has similar good properties like proper Calabi-Yau. First of all, why Bessel has the multiplication kernel? The simplest, of course, it is so-called one Bessel operator. This everybody knows since ninth or 10th grade class of your high school. So you can write d dx and take Euler or logarithmic version of derivation and write this spectral problem. And this spectral problem has exponential solution. You have this Maclaurin or Taylor development, and then the product of exponential for x and y gives you addition of x plus y, and then it is just immediately the simple hint. You can represent this exponential as the integral with a kernel given by this delta function, which in variable z is concentrated in x plus y. Or alternatively, you can write it as a residue in Cauchy form, and the Cauchy form also use this singularity x plus y point with respect to z. So you integrate by circle with mod z equal to x plus y, and then you can say, okay, my product of eigenfunctions can be represented in multiplication kernel way with the kernel which is rational, and this rational kernel is 1 over z minus x plus y. It's just, you can say, oh, it's just a trick, it's just nothing. Not so simple. The next case, when you take two Bessel. So as I explained in many forms this Bessel equation, which we call two Bessel. It is not exactly Bessel. It is better to call two Klosterman differential operators. But anyway, we can consider the spectral problem, and this spectral problem has a solution, which is a Bessel modified equation of degree 0, the first kind, with the corresponding changing of variables. So this is a classical Bessel solution. This is a solution of my differential operator. And for simplicity, to avoid to write this, I will use the wrong notation. It is usually this G, it is solution of usual Bessel, but I will denote in the same ways this solution of modified Bessel or degenerated hyper geometric confluence function. And this function has very beautiful, simplest representation is a power series in the power series form. The multiplication formula for these solutions, for this analytic solution, as I told you, it goes like the Sonin Gegenbauer, but Sonin and Gegenbauer, they wrote for real Bessel, not for modified Bessel. So the kernel here was square root of quartic, where x, y, and z, they had a degree 4, so it was u4 plus v24, etc. And the measure also has the z in nominator. But if you go to modified, you simplify not only series, but also integral representation. And this this kernel 1 over square root of this conic, which I denote by k here, we can check, and we can easily check that it satisfies to the following differential equation of the first order. This is equation with this singularity in front of d over dx. It means that where this kernel equal to 0, where this denominator equal to 0, this d module has singularity. So, and it satisfies this very nice condition that if you take x equal to 0, then we have 1 over z minus y. So it is also relates to this first to the first basic rational form. This it was just my first observation that this kernel satisfied the first order equation. And then what else I can say about this kernel? Well, if I take this solution of my two basic, then I can also consider the square of this function. It means not product g0, gx, g0, y, but take the diagonal, take x equal to y. And then it is very, very nice observation that this function, square of g, satisfy also to some beautiful equation. This beautiful equation, it is a symmetric square. It is there is operation on the d modules, there is operation on solutions. If you take the solutions of usual Bessel, then the square of Bessel is a solution of symmetric square. What is a symmetric square? I was again, it was my shame that after many years working with differential equations, I didn't know what the symmetric square, for example, of second order differential equation. Roughly speaking, it is the equation, for example, if you have the equation of the order 2, and you have two solutions, any two solutions, then you have an equation for which the product of these two solutions is equation. You have any two solutions of your equation, you take a product and you ask what equation I can write to have to have products of any pairs of solutions against solution. It happens that it is equation of order 3, and the coefficients of this equation uniquely can be uniquely recovered from the coefficients of the initial equation. For the case of Bessel, it is very nice and simple third order with respect to theta equation, and we can write the duplication formula in integral form for this square. So it is just again, if you go back to my formula and take x and y on the diagonal and take lambda say equal to 1 for simplicity, then this expression gives you the following integral representation. And you recognize in this representation just a convolution. It's a convolution formula, and the generating function which is given by my kernel, this generating function gives the series with so-called central binomial coefficient series. So the coefficient of this development, it is just a standard binomial development. But the central binomial coefficient is Cn. It is beautiful function which relates to so-called Catalan numbers. And it is not occasion. You can see in future that my computations will give a lot of combinatorially interesting integer sequences which are related to Catalan numbers, on to generalization of Catalan numbers. So this it is not exactly Catalan number. To have Catalan number, we should divide it 1 over n plus 1 anyway, and you can check that this is indeed the solution of this equation. And it gives you a beautiful interpretation of duplication kernel. It means that the kernel, it is a kind of kernel of integral transformation from 2 Bessel to its square. So we have this transformation, and the kernel, it's a kernel of this integral transformation. So it is interpretation very explicit. Okay, now I will show you some results which people usually call experimental mathematics, because many of these results are proven, but they obtained before with the help of computer, and some of them are not proven but obtained by computer and conjecture. Now I want to go to any n. Let's consider n Bessel, or my quantum equation for Pn minus 1, and then I write this solution of this equation in zero analytic first in my Frobenius basis, also in this series. Now, instead of square, I take n, degree n. And for future, I will put lambda equal to 1. First of all, I want to draw your attention that this solution has very interesting factorial representation for so-called Laplace transform, or sometimes people call it Barré transform. So if you apply to this function Laplace transform, you obtain the following power series with coefficients n times k over k factorial to n. And of course, you want to find the analog of the kernel. First, we can write easily the representation of the product in this series with respect to x and y. So it is not really very astonished and not very surprising that this product also have interesting binomial coefficients in x and y. Then we want to check if there is analog of good integral form for my solution, because my I didn't show you, but probably it was too quick. I didn't show you. I will try to write it. It maybe it isn't. So if you take theta 2 minus x psi 2 equal to 0, then this psi 2, which is, as you remember, this is sub 0 2 times square root of x, modified base. It admits the following integral representation, like exponential of x z plus 1 over z dz over z. So it's this. So you see that this is the function which depends on x and integration parameter z. For the case of it is g2 in this notation. If we take any n, then we should take exponential of multi-dimensional analog of this function. So we have, first of all, the parameter x, it is again x, like this. But here, I'm sorry, I made a mistake. It is not x, it is x. Parameter x, it is like this. Instead of z, you have this sum of n minus 1 parameters. Here it's z, here it's y1, yn minus 1. And instead of 1 over z, you have this product of n minus 1. And toric measure, here one-dimensional, here it is, so it's a measure on circle, and this measure on torus of dimension n minus 1. It is integral representation for n special solution. Then come back to our question about kernel. If I take the product gn x, gn y, so I can write it again in this integral form, and I want to find this k. First of all, I will write this k as a series. How to write this k as a series? I draw your attention that all these functions, they are homogeneous. So if I divide by z, then I can denote this k x over z, y over z, 1 as h. And I will check that h has the following development in this affine coordinate. So this x, y, z, I will consider like homogeneous coordinates in P2, and affine coordinates x and y, they give you the following h. And then I can try to write a singular loci for all n for k. You remember that singular locus for n equal to 2, it was very nice conic function x squared plus y squared plus z squared, etc. So if I take n equal to 2, I have this square root of delta 2, this one, and then go into coordinates, as I told you, go into squares. It means instead of x, I will write u squared. Instead of y, I will write v squared. And instead of z, I will write w squared. So I have this degree 4 analog of this coordinate. And this quartic, it is very nicely factorized. It's factorized like a product of u plus v. So you have a so-called Néron configuration. You have a triangle in P2 given by this conic in P2. This triangle. This is x equal to 0. This is y equal to 0. This is z equal to 0. I mean, you have 3 lines in P2. And then u, v, and w, they are lengths of side of this triangle. And of course, you have this full perimeter. And if you go into half perimeter, so you obtain that this is a square of area of your triangle times 16, because each factor gives you 2, 2, 2, because instead of half perimeter, you have this full perimeter. And this also you have instead of half perimeter minus u, you have this. So you have this coefficient 16. And this, what we call Néron configuration for n equal to 2. What's happened for any n? And it is interesting that for any n, you can write the following. First of all, you can write the following polynomial Landau-Ginzburg superpotential. So you can write polynomial in parameter y. This is a y n minus 1 big y's, and you have 3 coordinates in P2. So you have this function wn, which depends on n minus 1 y's. Special. It was not like previous for Calabi-Yau. You see, you have product of 1 plus y j and product 1 plus over 1 over yj. And coefficients x and y minus z gives you the hypersurface again in the product of circles. But now you have in front of this the same toric measure denominator, which is given by zeros of this Landau-Ginzburg type superpotential. So this hypersurface in P2 with respect to x, y, z. What is this hypersurface with respect to x, y, but hypersurface in x, y, z in P2? This hypersurface is very nice curve. This curve in P2 always have this triangle-like effect of x, y, z equal to 0. It's a coordinate triangle. And we have a rational curve of degree n, which corresponds to my n. And this curve has n minus 1 times n minus 2 over 2 double points. In the case of n equal to 0, we have no double point. But if we take n equal to 3, for example, for n equal to 3, we'll have one double point. And if we have any n, we have n minus 1 times n minus 2 over 2 double points. And this curve intersect this coordinate triangle in midpoints like it was for this conic for n equal to 2. So we have the following equation. If we write this equation starts with x to 1 plus y to 1 plus z to 1 plus other terms. But if we go to coordinates u to n, v to n, w to n, which usually people call Kummer transformation. So if we have this Kummer transformation and write u, v, and w instead of x, y, z, you obtain again very beautiful factorization of my locus for QNO. And this factorization, it is product of linear terms in u, v, and w with coefficients omega and eta, where omega and eta run over all roots of unity of degree n. So it's a beautiful analog of Ferron configuration. And now, look, it is fantastically a fantastic observation. I just want to say that I'm very, very proud that I have found this correspondence with Buchstaber Risk polynomial, so-called. So for n equal to 3, this is my polynomial delta 3. I don't write xyz like a factor. It's always xyz in all the cases. For n equal to 4, it is this polynomial. And this, it is, I repeat, for n equal to 2, my conic, you see. For n equal to 3, you can write this in this form also. And it is always a polynomial which has some special, if you write it as a polynomial in Z, it has a degree n, and the last term, it is x minus y to n. So such polynomials also appeared in Buchstaber Riess paper when they described so-called n-valued group law. Polynomial n-valued group law. It means that if you take the roots of this polynomial, that's what I want to show you. What is the root law? I go back to what I didn't show you. For example, for n equal to 2, two-valued group law, multiplicative law, it is just the following. let's take some set, let it be number set or some other, maybe even topological space. So we take set X, and then we have operation from Descartes product X times X, Descartes square, to symmetric square. And if we have this operation star, which admits so-called unit element E and inversion x to x minus 1, and this operation satisfies the associativity condition in the usual sense, what it means that element E is unit. It means that for any element x from x, if you take this operation with E from left and from right, then you obtain in symmetric square pair xx. So this is what people call condition of strong unity. And what is the inverse? In inverse, it means that if we have any element x, then we have operation x star x2 minus 1 and x2 minus 1 star x. This two set in symmetric square always contains natural or unit element E. So this is what people call two-value multiplication law. Example of this given, for example, the following construction, which gives you the simplest Buchstaben-Ries polynomial. Let's consider C with the addition operator. And we have this usual banal automorphism of C, just multiplication by minus 1. So we have epsilon square equal to 1, so epsilon equal to plus or minus 1. And then if we take quotient C over Z2, then this quotient admits this two-valued group structure. How it works? It works in the following way. Product of two x star y, two complex numbers, which gives you this modular automorphism class, these products of this x and y, it gives you two sets which is given by square root of x plus square root of y in square and square root of x minus square root of y in square. It is easy to check that the zero, it is unity, and inverse to each element C quotient to Z2, it is the same element. To check it, it is very easy. You just take change of variables, and from Z in C2, Z1, Z2, you go to symmetric functions of Z1, Z2. So we can consider the polynomial, which gives this law. This polynomial, it's a polynomial of degree 2, with second coefficient x plus y times minus 2, and the product of roots, it's x minus y squared. Then you can rewrite it, of course, also in this form of my conic, and also you can write it in discriminant form, but it is just to establish the relation, which what I told you in Kontsevich polynomials and in Buchstaben polynomials. And my two-valued multiplication form gives you by zeros of this, by roots of this of this equation, f equal to 0. How it works? It works like this. You take triple z, x, and y, this function, and put in this formula, put the product z minus x2 minus 1, and I remind you that inverse to each element, it is it itself. So it is just x times star y and x star y, and subindex 1 and 2, it means that you take from first place and from second place in your two set. So it is just a product of these simple differences. Z minus square root minus square and Z minus square root plus. And it is given by the simplest uh, verification. So in the language of Buchstaben and Ries, this polynomial defines the two multiplication log. In the similar way, now all polynomials which I obtained from zero locus of all polynomials which I obtained from zero locus of my kernel, all these polynomials define an valued group law. It means that now you have three roots of this, you have four roots of this, and etc. And you obtain n set symmetric degree. So you have x times x times x n times, and go to sim n of x. And with the same conditions, analogs of associativity, and with the same conditions of inverse, and the same condition of strong unity. So you have a structure of an valued group on C over on the correspondence C with action of automorphism degree n. Instead of epsilon square, you should take square root of unity of degree n, and then define the quotient by z sub n. So this is very nice observation. Now, what about duplication? It means what about the analogs of this Clausen duplication, which I showed you for n equal to 2. So if we go to diagonal, we have this square, and this square can be written as a power series, and the coefficients of this power series also have very nice sum of binomials, binomial coefficients in degree n. And this immediately you can recognize that it is just a Hadamard product, or it is so-called multiplicative convolution operator. So if we write the functions f and g in power series, then the Hadamard product, it is just a convolution of these two functions, which also can be written in this integral form, which you immediately recognize the form which I wrote for square of the n equal to 2, with a nice kernel related to central binomial. In the case of n Bessel, square gives you the convolution, this convolution of my function gn with some series which gives by the kernel, and of course you have analog of my function 1 over square root of 4 times x, which is hxx. What is this function? This function you can find in the following series. And for n equal to 2, you obtain this k2. For n equal to 3, you can find equation, and this equation has the following form. This equation annihilates k3. So this k2 is annihilated, you remember, by first order operator. For the case of k3, you have second order operator. So this k3 satisfies the second order operator. And this second order, it's a Hoyne operator. And this operator has the following property. If you write it in the form like Kontsevich wrote, in the form with operator T, then this operator is operator D X F D plus F prime D plus some constant. This it depends on the cubic F. F is cubic. It's a cubic. You can find, for example, for this K, you can find that this cubic and this square equation, it is defined. You can write it in theta form, you can write it like this. And for generic n, your K, as I told you, relates to period of this Landau Ginzburg superpotential. This. You remember before I denoted these parameters y, big Y, but here it is big X, but the type of Wn is the same. Parameters x small, y small, and z small, they are coordinates on P2 where the corresponding hypersurface can be considered. Okay, now we check that this kernel, multiplication kernel for G to N can be written in this form. This form was proposed by Kontsevich and Odesky, but they didn't compute it for GN. They just proved some general lemma how one can write the homogeneous kernels. And this, from the lemma for k equal to n, we proved that we also can find another hypersurface in torus. So remember, we wrote it before, like the solutions for this Landau Ginzburg. But we also can use slightly different Landau Ginzburg, which in some senses it is more nice because it will be close to what people wrote for Calabi-Yau correspondence for this Dwork type. It is not exactly Dwork type, but it's very like. You see, here we have the product, and here we have the product of 1 plus y's. But coefficients x, y, and z gives you the hypersurface depend on 3 parameters. And if you go to residue with this function in denominator, then you obtain the some function p, and we have checked it, and it is just a computation that this function pn, it is the same function like this series. So we have this kernel development as a period for this toric Calabi-Yau. This is a multi-variable formal series which corresponds to this residue. Okay, so I remind you that also it can be written like this for this superpotential. And then it is question how it relates to Calabi-Yau, because now we have this hypersurface. And for this hypersurface, we can check if there is a good Calabi-Yau compactification or not. And we can check that for n equal to 3, such compactification exists. We use, of course, known results. The known results that such toric hypersurfaces, they can be compactified to Calabi-Yau if they have Newton polytops. So we have Newton polytope and dual Newton polytope. So it means that Newton polytope is reflexive. So it's a polytope in 3, in the case n equal to 3. They are dual, and it means that there is a pair of these polynomials, which gives by these equations for n equal to 3, and they are Fano varieties, and these Fano varieties can be resolved in 4-dimensional space and give you Calabi-Yau after the resolution in 4-dimensional space from 3 in P3. So this conjectural pair of two mirror Calabi-Yau. For n equal to 3, our computations exactly correspond to this dual pair, this we check. But we don't know if it is true for any. Let's consider any, what we can say about equations. You remember that for n equal to 2, my kernel satisfies the first order equation. It's you remember this singularity. 4t minus 1. It is the expression which is 1 minus 4t. This one. For n equal to 3, this locus is given by this Buchstabe Ries. And this equation is degree 2. For n equal to 4, it's degree 3. And for n equal to 5, degree 4. Why I wrote explicitly all these differential equations for our kernel? Because for this case, it is they behave like good Picard-Fuchs equation. But if we take any Fuchsian operator which annihilate the kernel of degree n, Pn, then it is not so simple. First of all, let's consider the table of degrees and the corresponding MUM property. It means maximal unipot monodromy in the origin. If we take n equal to 2, you remember that the annihilating polynomial has degree 1, and the exponents, I mean, for this 1 minus 4 times x, it just no monodromy. But if we take n equal to 3, then we have order 2, and we have Jordan block with 0, 0, and it is 0, 0. Size of it times 2 times, so it's 0, 0. This, but it's okay. When we take exponent, we have a unit. For n equal to 4, again we have one block, 3 times 3. And for n equal to 5, we also have 4 times 4 Jordan block and MUM property. But for n equal to 6, what we have that to our Jordan block appears eigenvalue 1. So we have 0, 0, 0, 0, 0, 5, and this Jordan block and this one. Such block. For n equal to 7, we have second block with unity on the diagonal. We have times 2 times 2, and then 2 times 3 times 3, and 4 times 4, up to n equal to 9. And for n equal to 10, again a catastrophe, we obtain the new Jordan block, which has an eigen value 2, and of course it is just you have this block size 9 to 9, 5 to 5, and then you write just 2. Then for 11, it is, we have checked it, for 11 you have monodromy, third block 2 times 2 with 2 on diagonal. And it is a common property. What it gives you possibility to write Picard hooks for n equal to 5, but not for n equal to 6, because at t equal to 0 we have no more mum point. And what we can do for this? Well, we can do the same like physicists did it for Quintic and for Calabi-Yau GDEq. So for our 5 Bessel kernel annihilation operator, we can write Frobenius basis. This Frobenius basis starts with analytic solution, and this analytic solution has integer coefficients, and then logarithmic term for phi 1, and f1 has rational coefficients on, as it was for Calabi-Yau. Then for phi sub 2, you have logarithmic square, and of course,
Volodya, you disappeared.
Probably internet connection.
Yes, Женя, we lost not only slides, but Volodya also.
Среда будет какой день?
Следующая среда будет среда.
Какой день?
Ты имеешь в виду какой?
Сегодня у нас число, да.
Будет апрель.
3
А?
апреля. 3 апреля.
3 апреля.
Пожалуйста, да. А тогда я еще что-нибудь.
Хорошо?
Хорошо, это
времени уже мало остается, народ нервничает. Давай перенесем.
Нет, я могу сейчас, сколько времени сейчас? Уже времени совсем нет, да?
Ну да, в том-то и дело, да.
Нет, Ось, давай перенесем на следующий раз, я еще тогда что-нибудь расскажу, если вы не против.
Давай, хорошо, отлично.
Давай.
Okay, so we agreed that today we quit the talk and postpone the continuation to the next Wednesday.
Okay.
With some additional material. Thank you for your...
As a possible excuse, I will tell you something new.
Yeah, okay, it will be yes. Okay, thank you for your patience, but it is well.
Sorry, it's not my, it's not completely my.
Okay, увидимся через неделю.
Such thing happens. Volodya, thanks a lot, and we wait you in a week. Okay.
Bye.
Okay. Goodbye. Thank you for being here. Okay. See you next Wednesday. Goodbye.
Thank you. Bye.